Hi there. Welcome to the From Lab to Launch podcast by Qualio, where we share inspiring stories from the people on the front lines of life sciences. Tune in and leave inspired to bring your life-saving products to the world.
Hey everyone, thanks for joining the show today. I'm Kelly from Qualio, and I'm your host here at From Lab to Launch. We hope you enjoy the conversations on the show as much as we do. We'd love a quick review of the show on Apple or Spotify. It takes just a minute and it helps get the message out there. And if you want to be on the show, fill out the application linked in the show notes. We've had a lot of people reach out and it's been a pleasure to connect with you. Today, I am really excited to welcome David MacMillan, who is the James S. McDonald Distinguished University Professor of Chemistry at Princeton University and recent Nobel Prize winner. Professor MacMillan is an organic chemist who conceptualized and pioneered the field of asymmetric organocatalysis. I think I said that right. He launched and is now director of the Princeton Catalysis Initiative, which accelerates research collaborations between scholars at Princeton and industry. Along with numerous awards and commendations, Professor MacMillan has been elected a Fellow of the Royal Society and a member of the American Academy of Arts and Sciences. Most recently, in 2021, Professor MacMillan was named a co-recipient of the Nobel Prize in Chemistry for his work in asymmetric organocatalysis. I think you're really going to enjoy today's episode. Let's bring him in. Thank you so much, David, for making the time to speak with us today.
Yeah, hi, Kelly. It's my pleasure to get a chance to chat with you.
We love hearing about people's backgrounds, and you absolutely have a really interesting background. Can you take us through your journey to where you are today?
Sure. So you may be able to tell a little bit from my accent. I'm from Scotland. I was born and grew up just outside of Glasgow in a place called Bellsill. It's a very working class area. We were a working class family. My father was a steelworker. My mom was basically a maid. It's called a home help. And so I grew up there. I had a fantastic upbringing. It was truly wonderful. As I said, it was working class. We didn't have much money, but we had a huge amount of fun. It was just laughter every day. It was just one of those kind of places. And Scotland's kind of like that way. You know, people love to have a laugh. Anyway, so I wasn't really intending on going to university. In fact, I didn't know anyone who'd went to university, but then my brother, who was older than me, decided he wanted to go to what we call uni. And basically everyone thought he was crazy. My mom and dad thought he was kind of lazy because he didn't want to go straight to a job. And ultimately he went. And then on day one, after he graduated, when he got a job, he got a larger salary than what my father had as a steelworker. And so at that moment, my dad and my mom decided, you have to go to university. Not only that, you have to go and you have to do physics. And in fact, when I got to university, turns out I didn't really like physics and ended up moving over into chemistry. And it was ever since then, I've always been a sort of organic chemist.
Nice. Yeah, I wasn't a huge fan of physics in college either. Oh, that was a tough one. Tell us some more about conceptualizing and pioneering the field of asymmetric organocatalysis.
Yeah, it's great. You can actually pronounce it completely right. Most people don't really have a pen with it.
Well, I have to admit that I've been practicing all morning because I wanted to say catalysis. Yes.
Well, no, you're very good. Actually, it was kind of funny. I was in basically a dinner where the principal of Glasgow University said that, basically he heard that I'd made up this word, asymmetric organocatalysis, and said, maybe I should have got the Nobel Prize for literature because it was such a hard word to actually say, which I thought was pretty. But yeah, organocatalysis. Basically, when I was a postdoc at Harvard, there was two areas of catalysis. There was enzymes, which are the catalysts, which are in your body and in life. And there was metal catalysis. And with metals, they're often so reactive that they can't actually exist out in our natural environment. So you have to put them in this contraption called a glove box, where you shove your arms in those big gloves. You've probably seen them in nuclear facility type documentaries. And so I spent 2 years in this glove box, and it was, I learned an amazing amount in this lab called the Evans lab. After 2 years of this, I decided maybe it'd be great if we could come up with catalysts that actually existed outside in the natural environment. And so the idea was maybe we could use small organic molecules to actually do this type of catalysis. And so that was the original idea. It'd be great to do that. Unfortunately, I had no idea how to do that. And so when I started off my independent career at Berkeley, we didn't really start working on it because I didn't have any good ideas on how to do this. And then one of my graduate students, first year graduate students, asked me a really simple question. And I went to the board to sort of draw up the answer and had this sort of quintessential eureka moment of saying, wait a minute, this could potentially allow us to do this thing called organic catalysis. Maybe it would work. We tried it that afternoon and it worked. And it was just incredible. And then thereafter, I think the field sort of took off like gangbusters, and we were very fortunate to be a part of that. And there was just, the world sort of took over, sort of drove the idea into lots of different applications, which was incredibly exciting to see.
That is exciting. Boy, but there were a few pints lifted that night, huh?
Oh boy, yes.
Well, so tell us about the Princeton Catalysis Initiative. Where'd the idea come from? Where do you see it going in the future?
Yeah, the Princeton Catalysis Initiative. So the idea behind this was that when you walk into any university, you walk into any department, people tend to collaborate with the people right next to them, right next door. It's kind of like you bump into your neighbors, you talk to them, you end up doing collaborations. So we felt it was kind of, that's great. And that's traditionally how people do research collaborations. However, wouldn't it be great if people from all over the campus could sort of bump into each other on a sort of routine basis to sort of completely change the dynamic on how collaborations are created? Because if you think about it, most modern or progressive fields, they really sort of happen at the boundaries between two other fields where they kind of connect. That's where all the good stuff is. And so we were sort of trying to come up with an idea of how do we catalyze, for want of a better term, the way to get the faculty to talk to each other. So we came up with this idea called speed dating for scientists, which was kind of funny because when we first told the trustees at Princeton, they thought it was hilarious because they thought it was a sort of romantic thing. We're like, no. It's got nothing to do with actual dating. It's, can you basically get 40 faculty members in an auditorium for a day, and you tell them you have to stand up, you have to talk for 5 minutes and sit down again. And that way we're sort of ensuring that all of these different people from all over the campus get to hear each other talk about what they're excited about. And then at the end of this, they can chat, and then they can put in a one-page proposal. And if it's good, we'll sort of fund them. And so it's been an initiative that's also taken off like crazy. We wanted to raise enough money for over 10 years to maybe get to 100 collaborations. We've now raised almost $70 million. And at the moment, I think we're on schedule to get to almost 1,000 collaborations over 10 years. So, and there's already new fields that are sort of growing out of this. So it's been a really different approach to getting ways for scientists to effectively collide into each other, but it's beginning to sort of pay off, and it's been really exciting. And we're now beginning to see other universities are beginning to think about harnessing or using the same model.
Wow. And so it's human catalysis you've got going there.
Exactly. That's exactly. We're trying to catalyze interactions. That's the whole thing.
Oh, I love it. That's great. So then tell us about the MacMillan Group and what they're up to.
Sure. So the MacMillan Group is my research group. We're a big research group. We're about 42 members. Half of them are getting their PhD. Half of them are postdocs. And what they do is they're a really fantastic group of people to work with. And basically, they're working on a whole range of different research efforts. Most of it at this moment centered around how do you use light to either devise new chemical reactions using light or new technologies to understand biology using light. So we basically work in these two different areas. But all of it is sort of anchored around using visible light to allow you to do completely new things, which will hopefully impact things like medicine, materials, and other areas where catalysis and chemistry is important.
Yeah, we were chatting a little bit there early on about, the incidents back in the pharmaceutical industry where, different types of molecules and being able to control those things in the manufacturing process. I too have spent a lot of time with my arms in, you see that a lot in the pharmaceutical manufacturing industry, but I don't think people realize the complexities of trying to control those kinds of manufacturing, to get the same product coming out the other end every time. So It's good to see the innovation.
Yeah. Now we've been very fortunate. And a lot of our technologies now, and the ones that we've developed at Light, are now being used by medicinal chemists to make drugs. And that is one of the greatest parts of being a researcher, is not just discovering things or inventing things, but seeing adoption. And you see adoption across areas where it's very noble. And if you think about it, there's not many more industries where it's more noble than actually making medicines for human beings. They're really noble people that work in pharma. And so for me to see them being adopted by those industries is really just tremendous. It's just a really fantastic thing.
That is fantastic. One of the other thoughts I had as I was reading about some of the research and things you guys were working on too is the idea of the supply chain and having come out the other side of, the COVID pandemic, or maybe we're not all the way out yet, who knows, it really exposed around the world everybody's vulnerabilities to supply chain. And, one of the things I always heard a lot was, why can't we just make those things here in the States? Like, well, you can, but then there's these environmental impacts, that tie directly into like the metals you were talking about from the catalyst perspective and whatnot.
Absolutely. So that's where, I think catalysis at the moment is used in 90% of chemical reactions around the world. And it basically makes up for 35% of the world's GDP is based on catalysis. So sustainability is enormous if you think about it. And catalysis allows you to become more sustainable. But you also have to make the catalyst sustainable as well. So that is one of the sort of benefits that we had with developing these small organic molecules, because as you know, and I'm sure people who listen to this show know, organic molecules go right back into the life cycle. They're completely recyclable. So you don't have that problem, which is a nice feature, especially when it comes to waste or getting rid of basically byproducts of these manufacturing processes. It's really important that they become more and more sustainable.
Yeah, the environmental impacts there are I'm not sure they can even be quantified at this point.
Yeah, absolutely.
Well, congratulations on your achievements, such as being elected a fellow of the Royal Society, becoming a member of the American Academy of Arts and Sciences, and most recently, being a co-recipient of the Nobel Prize in Chemistry 2021 for the development of the asymmetric organocatalysis. Those are incredibly outstanding achievements. How does that feel? Was this something that was kind of on the radar for you from a, career dreaming perspective?
No, absolutely not. And it's kind of one of those things where people say, are you sure? Did you really not know? And I think no one was more shocked than me when I won the Nobel Prize. And probably no one was more ill prepared than I was, because it was just, you wake up one morning and the world, your whole life has changed, and it's sort of changed permanently. And you don't sort of realize it until it sort of happens. So the first 2 or 3 days was such a whirlwind. It was just extraordinary. And then you think it's going to sort of die down, but at least so far, the way that people interact with me, the requests that you get, et cetera, just continually enormous. And I'm sort of hoping after the first year, it'll sort of die down a bit. I don't know if I've got the capacity to keep going at this sort of rate of sort of interaction with people. But I mean, but at the same time, it's fantastic. It's an amazingly lovely thing. And you also get opportunities to do lots of things that you wouldn't have got to before. Some fun, some important, and some with respect to being a responsible citizen. So across the board, it's just been a really remarkable experience.
So wonderful. Well, if you could go back and tell yourself something at the start of your career, what would that be?
Yeah, that's a really interesting question. I've spent a while thinking about this, and it's kind of weird, and this is probably not a very satisfying answer, but I think for me, I would probably not go back and tell myself anything, because I feel like I've just been inordinately fortunate. And when I sort of think back to my life and all the different parts that had to sort of come into being to sort of get me to this point in my life where I'm having a fantastic time and have an amazing family and an amazing group, I feel extraordinarily fortunate, incredibly lucky. So I feel like there were so many sort of forks in the road I could have sort of taken differently, where I mean, who knows where you would end up, but I certainly wouldn't be here. And so for me, I almost feel like I wouldn't do anything. I would actually just say, yeah, just do it the way you did it. There was a lot of mistakes along the way, a lot of failures. But failure, and it's a little obvious to say this and cliche, but failures are great. Failures are what experience is made of. And I think you have to have all those failures to sort of appreciate success. Maybe that's why I'm a Scotland soccer fan, because we have so many failures that whenever we have success, it's amazing. But yeah, I think it's just as important as being successful as sort of hitting those bumps in the road.
Definitely. I totally agree with that too. And it's funny because people don't, publish a lot about the failures, but I think we should do that more. I think we should talk about those because they really are opportunities for learning.
Yeah. I mean, if you think about learning, I always think that when you give a good lecture, you've got to sort of introduce adversity into your lecture, right? So that it's like watching a movie, like a good movie, a lecture's like a good movie. You sort of, the audience goes along for the ride and there's the ups and downs. And adversity is a critical part. You have to understand the problems before you can understand the successes. And that's what makes it exciting to have an appreciation for it. So absolutely, I think adversity is one of the parts that really makes science so enjoyable. in a weird way, because it's that sort of, when you get this achievement, you get something to work, you get that chemical reaction you've been trying to do for 2 years, and then suddenly it works. That's an amazing thing. And it's an amazing experience. So you have to have that tension for it to really get the full appreciation of the science.
Definitely. That's quite a story. Well, so where can people go to learn more, follow along, and connect with you?
Well, the easiest place is my group's website, which is, if you just go to Princeton and type in my name, and my group's website will come up. We have all the publications there, as well as summaries of what we're doing. It's very technical, so just be warned, but absolutely you can sort of find out what we're doing, what we're up to, the research areas that we're involved with. And we do have some more sort of cliff note versions of what we do there as well, if it's a little bit less technical for people, if they're really interested in finding out more.
Thank you so much for your time, David. We appreciate it. It's been a pleasure.
Thank you, Kelly. That was great.
Thank you for listening to this week's episode of From Lab to Launch, brought to you by Qualio. If you like what you've heard, please subscribe and give the show a positive review. It really helps us out. For more information about Qualio, our guest today, or to be a guest on a future episode, please refer to the show notes. Until next time.